All right, good morning. So I've pushed back ODP 215. That will open up on Monday and be due on Tuesday. The reason being that it relates to deleting from a binary tree, and we're not going to talk about deletion until tomorrow. There's no urgency on this because, you know, hopefully deletion's the last piece you'll put in for your PA4. But the README is still available on the server, so if you want to look at it and work on it ahead of time, you're welcome to, but we're not going to go over the piece of deletion that the ODP deals with until tomorrow. So that will officially open on Monday. Any questions on 212, which you just finished? All right, so let's go through recursive tree traversal in a little more detail. So we put together an algorithm yesterday for in-order traversal. So in order is left node right, right? So we traverse the left subtree, we access the root, and then we traverse the right subtree. So here's the code we had. Left node right. That's in order, and it was 4 lines of code, right? Traverse the left subtree, print the root data, traverse the right subtree, and then the special case of see if the tree is null, and if it is, just don't do anything. 215 does involve searching, but it's a search which is used as part of the delete algorithm. We'll go through a different way to search binary trees in a little bit. That's unrelated to 215, ODP 215. All right, so this was the in-order traversal, and remember we have 3 approaches. Left node right is in order. Node left right is called pre-order. And left right node is post order. And the prefix here refers to when we print the root node data. If we do it in the middle, that's called in order because your data will come out sorted. If we do it first, that's pre. If we do it last, it's post. So this is our in order traversal. What if we wanted to do post order? That's it. So to do LRN traversal, what do? Do LRN on the left subtree, do LRN on the right subtree, and then print the root data. And the usual edge case, if the tree is empty, don't do anything. So there's post order, there's in order. And you can imagine what pre-order would look like, right? Exactly the same variation, except we would print before we did either of the traversals. So those are recursive traverse algorithms. And let's take a look at this in GDB, just if you decide to go that route. So compile it up as usual. And let's put a breakpoint at left node right. And I'm going to say run. So I've called my insert function a bunch of times, and I've built up my tree, and now I have this tree whose root is, you know, given by root. So there's the value of root. Root points to a node that contains a 10. The left child of that is a node containing a 1. The left child of that is a node containing, or the right child of that is a 5. The left child of that is a node containing my big ridiculous negative number, right? So you can go in ODB and you can see what your tree looks like, right? I know it's got a root of 10. On the left is a tree with a root of 1, and that root of 1 has children, which is, you know, negative 11 to 23 on the left, 5 on the right. And you can draw a picture of this and make sure that what's going on in memory matches what you intended. But let's go ahead and let's call our left node right function. Now I'm going to use step to go into that, because if I say next, it will not come back to my prompt until it's returned from that function call. So I'm going to step into LNR, and it checked to see if root was null, and it wasn't. So now it's going to call LNR again, so I'm going to step into that, and it's going to check to see if root is null, and it's not, so it's going to call LNR again. And it does that, and it passes this root, right, 320, which was this node containing a 1 with a left child and a right child. And I'll step into LNR on the left child, and now I've called this with a left child that is null. Alright, so where the heck am I? So you can say BT, that's short for backtrace, and you will see what's called a call frame, right? Or a hierarchical history of all the calls that you've made. So from main, line 33 of insert.c, I called LNR, which called LNR, which called LNR, which is where I am right now. Right now I'm inside LNR, line 85 of insert.c. So my most recent call, the place where I am right now, that's frame 0, right? So that's that right there. But this was called from, you know, line 86 of insert, which was called from line 86, etc. So you can get a picture of where you are in the hierarchy of calls, right? Now this function, you know, the main thing LNR does in the beginning, if the root's not null, it calls LNR on a subtree. And I can see what LNR was called with in each case. And if I look at these roots, I'll see, you know, the root of successive subtrees in this call hierarchy. So if you want to try to understand these functions from the point of view of what's actually happening, what's being executed, what's being called from where, right, GDB can help. Really big sheets of paper and a good pencil with a nice eraser will help a lot. But at some level, you don't want to go too far down this rabbit hole, at least not on a regular basis. It's good to do a few times, right? When you're feeling like, okay, I want to see what's going on behind the curtain, jump into GDB, start doing this, draw some pictures. But when we're writing recursive code, we're usually not thinking about this. Okay, we need kind of a two-sided mindset. The mindset where we understand, okay, I'm calling this function and these things are, you know, happening in response, and now I'm starting my function again with a different argument, right? That's useful at some level, but mostly we're kind of going on faith, right? We're kind of going with the idea that what does this function do? Well, it calls itself on the left subtree, it prints the root, it calls itself on the right subtree. And we're thinking of it like that when we're writing this, and mostly we're thinking of it like that when we're debugging it. Now, if something really strange is going on and we have to get down to, you know, examining memory inside the debugger, then we might need to go to, you know, the level where we're actually looking at what particular memory locations are passed and where we're being called from and where we're going to return to and so on. for the most part, we're going to sort of think of this from a higher level. But if you want to go into GDB, backtrace is a useful command to see this call stack. All right, so that's our traversal code. And I want you to start using recursion when you're writing up PA4, right? Starting with the traverse code. If you've already implemented it as a loop, go back and re-implement it using these recursive calls. And there really is 4 lines of code. And it's a fairly benign way to break into recursion. All right, so questions about that? Otherwise, we're going to go on to search. All right, so let's look at searching. So here's a random tree, and let's say we want to search for some number in this tree. We talked about how to do this iteratively. We have a temporary node pointer that we initialize to the root, and whatever number we're searching for, so let's search for, num. We compare num to the root. And if num is smaller, then we change our temporary pointer to be the root of the left subtree, and we go back to the top of our loop. And if our num is bigger than 40, then we set our temp pointer to be the right subtree's root. And if our number is smaller than 45, then we would change our temp pointer to be the left subtree's root. And if our number was bigger or smaller than 42, we would change our temp pointer to be the root of the left or right subtree, which would be null. And that would tell us the number's not found in the tree. But if at some point we get down to a root and the number matches the root data, then we have found it. So that was the iterative approach. Let's see what this looks like recursively. So here's the idea. There's exactly 3 places that our number could be. So if our number is equal to the root data, then we found it. Return a 1. But suppose we're not looking for a 50. Suppose we're looking for a 40-something, or an 80-something, or a 90-something. The thing we are looking for will be either in this subtree on the left, or this subtree on the right. Now, it may not be found. But if it is found, it's going to be in one of these subtrees if it's not the root. And we know exactly which subtree it could be in by comparing our number to the root of this original tree. So now we can make a pair of statements. If our number is less than the root node's data, let's just search the left subtree. Search root arrow left for our number. And if that search says I found it, then we found it. And if that search says I didn't find it, then we didn't find it. So we can simply return whatever this function returns. Yeah, you got it. But if our number is bigger than the root node's data, We don't want to search the left subtree. We want to search the right subtree. And I'm just assuming that you know, that there's nothing in the tree twice, right? So let's not worry about edge cases like that. So your number is either equal to the root, it's less than the root, or it's bigger than the root, right? We don't actually need to have this if statement, but it might make things clearer to have it. But, you know, if it's not equal to the root and not less than, we know it's bigger than the root, so we search the right subtree and return that. And this is almost your whole search algorithm. And it's 1, 2, 3 lines of code. So there's one edge case we need to check still. What's the edge case? Well, the root data can't be null, but the root could be null, and that's the edge case we're looking for. So if I try to search an empty tree, this will segfault. Now remember, root data is just an integer, so that's always going to exist as long as root exists. But if root is null, this will segfault. And there's nothing in here that ever returns a 0, so we're clearly missing something, and it's the same thing that we're missing as the null case. So if root equals null, there's nothing in our tree. Obviously our number is not found in our tree, so return 0. Awesome. So there's your whole search function. So if the tree is empty, it's not found. If the data is at the root, it is found. Otherwise, call yourself recursively to search either the left or right subtree and return whatever that call returns. And that's it. That's your search. Now there's a lot of weird stuff going on behind the curtain here, but in terms of logically thinking about what this algorithm does, it's pretty straightforward. It's really the idea, if your tree's empty, your data's not in there. If your data is at the root, it is in there. Otherwise, see if it's in the left subtree or the right subtree. And if it is, then it's in the whole tree. And if it's not in the left and it's not in the right, then it's not in the original tree. Make sense? It is pretty sweet. Yeah, it is exactly like a binary search. All right, let's go ahead and do insert. And so again, if you start with some tree like this and you want to insert a new number, and I'm going to assume the number's not already in the tree, so we won't worry about, you know, edge cases where you're trying to put something in that's already in there. But suppose this is what our tree looks like, and suppose we're trying to insert, I don't know, 75. Let's see, when you return search, if the left or right is null, won't it segfault? I can call with a null argument here. If root left is null, that's okay, because when I call search and my first argument is null, my first statement will say if root is null, return 0. That will just return a 0. And if the right is also null, this will return a 0. The only danger is if I'm inside here and root is null and I try to access a field that root is pointing to, but I'm never going to execute these statements if root is null, because that's going to kick me out. Does that make sense? We don't really define undefined, I guess. Null is a valid thing. It's basically a 0, right? It's just a reserved value that's guaranteed never to be the value of an actual pointer. So yeah, it is definitely defined. All right, so let's insert a 75 into here, and we did this iteratively. Last week we wrote some code in insert function, and the idea was similar to search, or have a temporary pointer sitting at the root, compare what you're inserting. Since 75 is bigger, change your temporary to the right child. And then compare what you're inserting to the root, and since 75 is smaller, we would change our temporary pointer to the left, except the left subchild is null. So at that point, we would simply change the left subchild of 80 to be our new node, 75. So that was an iterative algorithm, and it basically, bounces down just like we're searching for something. But when we get to the point where we would normally give up on our search, we go ahead and we add our thing there. But we can think of insert recursively. 2 steps. We want to insert a 75. Since 75 is bigger than 50, we know we're going to insert it somewhere in this subtree on the right. Well, how do we do that? Let's call our insert function. Suppose I want to insert a 23. 23 is smaller than 50, so let's insert 23 into this smaller subtree on the left. How are we going to do that? We're going to call our insert function. So this is going to look mostly like 2 lines. So if our number is bigger than the root data, insert our number into the right subtree. If our number was less than the root data, insert our number into the left subtree. And that's most of our insert function. Those 2 lines of code. So either insert into the right or insert into the left. Alright, so what's the edge case here? Empty tree, right? If the tree is empty, then we cannot say, let's insert in the right subtree. There is no right subtree, and if we try to access root right, that's going to segfault. So we have an extra case up here. If our root is null, and we have to check that even before we check to see if root left or right is null, because if root was null, yeah, so if we said root left, That would segfault right there. But if we take care of this case right here, we can avoid ever doing any of these things. So what do we want to do if the root is null? We want to create a root of an empty tree. If our tree looks like this and we're trying to insert a 23, the result should be a tree containing a single node whose root is 23. So here's where we do our usual things. So new equals malloc. New's data should be equal to the number we're inserting. Its left and right child should be null. Children, not childs. And here's the tricky thing that I mentioned about needing to have the insert function return a tree. Because if I call insert and I pass null here, when I come back from insert, I want my caller to have a tree containing a 23. So we need this insert function to return a root. It's going to return a struct node star. And then in this case where the tree was empty, we can just return new. And so there's your edge case. If the tree doesn't exist, if the root is null, make a node, set up the data left and right fields, and then return that node as the return value from insert. And so in main, whenever we insert something, we're going to, say root equals insert root, comma, whatever number we want to insert. And we initialize the whole thing by setting root equal to null. So down in our code, when we decide we want to insert into the right subtree, right, this is going to insert into the right subtree. Return your original root. I made a typo in the previous section, so if you watch the video, I think I returned the result of insert. Let's just return root. So normally this business of returning the root of the tree is kind of a no-op, right? Because in general, if we insert into a tree, the root's not going to change. The only exception is when you go from an empty tree to a tree containing one node, and in that case we need to change the root, so that'll be returning something different from what we received. But otherwise we just return the root. And again, since we're returning, we don't really need to have this if statement in here. But I would put some comments in or something, right? So if the number is bigger than the root, insert it on the right and return the result of that. Otherwise, insert it on the left and return the root. Let's see, if root right is null, if you add a new node, do you link the null to the new node? So if root right is null, yeah, I missed something here. There we go. Thank you. All right. If our number is bigger than the root data, go ahead and insert your number into the right subtree and set your current root's right child to what you got back from insert. That's super critical. Thanks for pointing that out. All right, so big typo there, a YIPO. And if you're inserting the left subtree, right, insert your number into root arrow left, take what you get back from that and set root arrow left equal to that. So now the effect is, if we're inserting a 75, we're going to put that somewhere into the subtree. We're going to take the root of the tree that we get after we insert it, and we're going to make 50 point to that on the right. And that's going to handle the particular case where, for example, we want to insert a 75 on this tree. Well, our number is bigger than the root data, so we're going to insert 75 onto the right. Well, root right is null, so we're going to call insert with a null tree and a 75. And that's going to create a new node, 75, and return the value of that as the value of the insert function. And so in here, we'll set root right equal to 75. So that's what ties them together. And then when we're done, return the root. All right, good. Any other questions about that? All right, let's look at the cost of all of this. So this is very easy to write once you're comfortable with recursion. This is a more direct implementation of what we usually think of for doing a search or an insert or a traversal or things like that. And once you get in that mindset, you can think of more and more things recursively, right? For example, how do you print the contents of a linked list? Well, print the first node. That's easy. That's just, sentinel, arrow, next, arrow, data. And then print the rest of the list. Well, you can just call your print function on, the rest of the list. How do you find the largest number in an array? Well, look at the first number in the array and compare that to the largest number in the rest of the array and return whichever one is bigger. Well, how do you find the largest number in the rest of the array? Just call your largest number function on the rest of the array. So you can start to think of lots of things in terms of recursive algorithms. And it's a very powerful way to do a lot of fairly complex things in computer science. The downside to recursion is it can be expensive, right? Anytime that you make a function call, there's a lot of overhead involved. There's a lot of state information that needs to be saved. For example, when I call any function, I have to save the program counter, right, at the CPU level. I have to save where I am in my code so I can return to it at the end of the function call. I may have to save the values of registers. I may have to save information about local variables. And all of that takes time and it takes memory. And if I make 1 million calls to myself, there's a good chance I'll run out of memory. And I may run out of time. And so you get into, Stack Overflow issues. For a tree, right, each time that we call our search function, we call it on a subtree, which is either the left or right subchild of our current tree. Well, when you go from a tree to a subtree, what happens? The height decreases. So remember, the height of the tree was the maximum depth of a node. Roughly speaking, it's the number of hops from the root to the deepest node. Well, in this tree, I can go 1, 2, 3, 4, 5 hops to get down to this 95. If I look at the right subtree, that has a smaller depth. My maximum number of hops from the root of this is 1, 2, 3, 4. If I look at this tree, the maximum number of hops is 1, 2, 3. And when I get down to a tree with a height of 0, its left and right children are null. And when I call this with a null argument, it's not going to recurse. It's going to come back right away because of this check for an edge case. So if you put that together and think about it, the deepest I'm going to go recursion-wise is bounded by the height of my tree. So at any point, if I do that BT command, that backtrace command in GDB, and my tree had a height of 30, I should never see more than 30 call frames. And that's not a problem. Calling a function, 30 levels deep is easily managed by, most any reasonable processor. But if I don't have an edge case check, and I start calling myself forever, I can run out of resources. More likely I'll segfault. So if I did what I suggested, to print the contents of a linked list by printing the first node and then calling my print function recursively, and I had 1,000,000 nodes in my linked list, my recursion would go 1,000,000 levels deep. That very likely might run out of resources. Right? I could overflow my stack space, and I could end up crashing my program or my system. So we want to be a little careful with recursion and make sure that we're using it in a situation where it's not going to blow things up. The other issue is time, and we'll talk about dynamic programming in a couple of weeks, and this will be a way to deal with some of the time overhead associated with recursion. But for now, we're not going to worry about it too much. We're just going to happily keep wallowing into recursion land, and let's look at the height function. So you want to find the height of a tree. And we said it's the depth of the deepest node. So how do you find the deepest node? Well, you could traverse your tree, and as you move through and visit each node, have a global variable that keeps track of how deep you are. And each time you get to a leaf node, if its depth is bigger than the biggest depth you've seen so far, record that as the new deepest you've gone. And when you're done, whatever the deepest node was, that's the height of the tree. Okay, that's an iterative algorithm. It's kind of a pain to code up. There's a much easier way to think about height. So what is the height of this tree? It is one of the following two things. It's either one more than the height of this tree on the left, or it's one more than the height of this tree on the right. Whichever one is bigger. And that kind of makes sense, hopefully, right? Because, however many hops it takes to get from the root to this node, it takes one fewer hop to get from the root of this subtree to that node. And so whatever the deepest node is in here, for example, this is one of the deepest nodes, the number of hops from this root to that, if I add 1, I find the number of hops from this original root to that. So the depth of this node in my original tree will be 1 more than its depth in this subtree. So here's an easy way to find the height of a tree. One line. Find the height of the left subtree, the height of the right subtree. Find the larger of those two, add 1. That's the height of your tree. It's a purely recursive definition. Right? I'm defining the height of a tree in terms of the height of subtrees. It's 1 more than the height of the tallest subtree. And don't get tripped up on max. This is pseudocode, so write an if statement or something to find the largest of these two numbers, add 1 to it, that's the height of your tree. The usual edge case is missing. If our tree is empty, we cannot look at the left or right subtrees. Those will segfault. So we have to explicitly handle the case where the tree is null. And remember, the height of an empty tree is -1. And that's one of the reasons we have the height of a minus tree defined to be -1, because it makes this algorithm work. So if I have a tree with just a root node, the left subtree will have a height of -1, the right will have a height of -1. 1 plus that will be 0, the height of this tree will be 0, which is what it should be. This is your base case that makes your inductive proof of the correctness of this algorithm work correctly. So questions about that? So these algorithms are extremely simple. The challenging part is the whole idea of recursion. And if recursion is new to you, then this is probably really confusing, right? At some level at least. But the algorithms are simple in the sense that, you know, they're 2 or 3 or 4 lines each, and they don't really seem to do a whole lot, right? But that doesn't mean that understanding them or writing them or making them work or debugging them is going to be easy, right? It's probably going to be the opposite. But you want to hop in and start writing some code like this and get it to where it starts working. And again, the traversal code is probably the easiest place to start. Just write you know, you can take the code we did in class, or you can just cobble together a tree by hand and try to write an in-order traversal algorithm that's recursive. So you write the if statement for max above the return somewhere. You know, if height of tree left is bigger than height of tree right, then return 1 plus height of tree left. Otherwise, return 1 plus height of tree right. Or maybe save those in variables so you don't call the height function multiple times. Or make a function that takes 2 integers and returns the largest, and pass those 2 arguments to your function or something. But just think of this as pseudocode. So try to do the recursive traversal, and then I would say try to do a search function, right? Because search doesn't require you to modify anything. It's purely traveling down the tree using these recursive mechanisms, so something like that. And then try to do insert. And insert is where we're actually modifying the tree, right? So we're changing what's being pointed to by the root and returning that as the insert value. And that part gets a little weird. But once you have insert working, then there's nothing stopping you from like finishing this whole thing, except for tree deletion. All right, and balance, right? Balance we talked about last week. It's actually defined recursively. So your tree is balanced if either the tree is null or all 3 of these things are true, right? The difference in height of the left and right subtrees is less than or equal to 1, and the left tree is balanced and the right tree is balanced. Right? So to write the code for a balanced function that takes a tree and returns, you know, 1 or 0, you're going to need to call the balance function on the left and right subtrees. It's a recursive definition. Your implementation will be recursive code. And as usual, there's an edge case, and often the edge case is when the tree is null. If a tree is empty, it's balanced. So in the beginning of your balance code, you would say, if, root equals null, return true. Otherwise, call your height function on left and right, compare the difference. If the difference is bigger than 1, you can say false right then, it's not balanced. If the heights differ by less than or equal to 1, see if the left tree is balanced, see if the right tree is balanced. If all three of those are true, you can return true and say, yes, this tree is balanced. Anything else, return false. Alright, so that leaves deletion. And we'll talk about deletion from binary trees tomorrow. Deletion is the one binary tree algorithm where we actually have to do some work, right? Most of this stuff, we don't really do any work. Inserting into a binary tree, other than the edge case where we actually create a node and store the data, we're just making some function calls, right? Which is kind of typical for recursive code. It usually feels like you're kind of cheating, like you're not actually doing anything. But tree deletion, we're going to have to actually do some work. And the recursive part of deletion is easy. Suppose you want to delete something which is smaller than the root. Well, we know the thing has got to be in the left subtree, so just call your delete function to delete it from the left subtree. And if you're deleting something which is bigger than the root, just delete it from the right subtree by calling your delete function. So all the work of deletion comes down to how do we delete the root of a tree. And that's going to take a little bit of doing. So we'll play with that tomorrow. And that will involve a step, which is what ODP 215 has you write. So it's not a bad algorithm, but it's something that takes a little bit of actually moving around your tree and writing some code. And that'll take care of deletion. And we'll do that tomorrow, and then we'll probably talk a little bit about balance. Or I may leave balance and come back to it. So that's our plan for tomorrow. Finish up deletion from trees, and then maybe talk about balance. And then next week we're going to change gears and talk a little about sorting and searching. And then we're going to talk about dynamic programming, which is a lot more recursion, and will take us into PA5 eventually. And then we'll come back and we'll talk about other variations on trees and binary trees. All right, have a good afternoon. Enjoy watching the landing of Perseverance if you're going to do that. It looks like it's an hour and 5 minutes to touch down. Cool. Have a good one. I will see you next time.